test. Oh, perfect. So as I said, I will take this opportunity to present myself. I'm a user of Gentoo since 4 years, more or less, and since 2 months, I'm part of the Gentoo staff. And last year, I did a Google Summer of Code project for Gentoo, which is called numbench, a benchmarking tool for Gentoo. And now, 1 year later, I will present my results. So let's spend 2 words about numbench before I can explain what this is. This is a tool targeted for Gentoo, so this is a specific benchmarking tool for Gentoo. This won't work on OpenSUSE or Debian or Windows. Does it make sense to do a benchmarking tool for just one single operating system? In my opinion, yes, it does, and I will explain this later. It's a tool written in Python, which is my preferred language, and it can test many different things. It can test, so benchmark, implementation of standard APIs. Why? I will explain this later. It can test single libraries, it can test whole programs, and it generates nice HTML pages with plots and results. Okay, so this is the outline of my talk. At the beginning, I will explain why did I such a tool for Gentoo. Then I will show some implementation details, and later on I will show some nice results, and finally we have an outlook. So in order to explain why I did such a benchmarking tool, I will explain a bit how the numerics libraries work. So we have a BLAS, which means basic linear algebra subroutines. It's a standard APIs for numerical libraries. It provides interfaces for basic operations like matrix multiplies, matrix vectors multiplies, vector additions, triangular solvers. And we have an example here. It's a Fortran interface, so it's ugly. And this is just a routine for computing a matrix vector multiply in double position. You see everything is a pointer. It's ugly, but it's a standard. So there are lots of libraries that implement this standard. So if you want to use a linear algebra package for computing things, most probably you will use some implementation of these APIs. Or maybe such an implementation will be a backend for your library or your tool, but you will somehow use this. So it's widely used, not only for scientific operations. We have lots of packages, lots of programs that use such an API. And as I said, many implementations exist, and every implementation normally is targeted for a specific operating system or a specific architecture. So in Gentoo, we have many packages that install at least one implementation of this API. For instance, reference is the reference Fortran implementation. Then we have Atlas, OpenBLAS, Eigen. MKA, for instance, is the Intel closed source implementation. And I have to say that most of these packages install many implementations. For instance, MKL installs 18 different implementations compiled with different compilers, with different flags, for different architectures. Atlas, for instance, installs 2 implementations, a serial one and a multi-threaded one. So we have lots of possibilities. And because we are Gentoo guys, we know that Gentoo users have the choice. They can install different packages, or they can install, so they can compare the performance of one package with different implementations, or what happens if we install a package with different CFLAGS. We are compiling these things. So we can do lots of things in order to compare how well a library is, or compare one library against another one. So my benchmarking tool will do exactly this. So it's a tool that is capable of comparing different implementations out of different packages. It's a tool that is capable of using Portage to compile a package with specific environments, or to run a benchmarking program with different environments. So just everything I said here is portable to the LAPACK world. LAPACK is another standard API in Fortran, which is used for more advanced linear algebra operations, general solvers, eigensolvers. So this is a nice example. We have standard APIs which are widely used, and we can compare different implementations, or just the same implementation compared differently. But we also have, for instance, FFTW, which is not just a standard API, it's a library. So we just have one implementation, and we can compare this package with different CFLAGS, for instance. Or we can run the same implementation with different environments, with different number of threads, and we can compare the results. And then we also have Metis. This is another nice example. Metis is just a program that does mesh partitionings and graph partitionings, and we can compare it with different flags. So we have a set of questions. Do different implementation behave differently? Does an implementation behave differently if we compile it with different CFLAGS? Does the compiler play a role here? So in order to answer these questions, we do benchmarking. I will speak here about performance benchmarking, but I want to mention that NumBench is a perfect tool also for other kinds of benchmarking. I also did accuracy benchmarking, and I want to say that there are lots of things that can be benchmarked, not just performance. So it's not just numerics. Now, I will present here some implementation details. We have a main script, which is NumBench itself. It does a lot of things. Then we have different modules. We have, for instance, a module for BLAS, which tests different BLAS implementation. We have a module for LAPACK, for C-BLAS, for C-LAPACK, and also for accuracy benchmarking. So we have a lot of modules. Every module is related with a benchmarking program. The benchmarking program is a piece of software that usually gets compiled everything we want to test an implementation. So for instance, in the case of BLAS and LAPACK, we have a software which is written using the BTL library, bench template library. It's a C++ program. It gets compiled and linked against new implementations of the library, and it gets run. So we run this benchmarking program. It outputs some date files, and then the module can tell the main script how these date files are done, and the main module, the main script can output them. Here I had some more details, but this doesn't work very well. So I try to explain what NumBench does, what the modules do. So NumBench basically does the input parsing. Input is done through an XML document. Then NumBench also has a Portage interface. So the user's input say which packages have to be tested, and NumBench just installs using Portage those packages. Then NumBench also has a report generator, so for HTML, and also has a log manager. Everything which is done in NumBench is logged. Then you can see that NumBench has different modules. Here we just have three: a BLAS module on the left-hand side, then a LAPACK accuracy module, and on the right-hand side we also have a Metis module. Every module has a benchmarking program, which is different from module to module, usually. most of these benchmarking programs are done with the BTL, as I said, and they output some date files. Each module basically does 5 things. Namely, it receives some input from the main part. There is a section of the XML document in the input which is for the module. Then the module just compiles the, before it can do this, it must search for implementations. As I said, every package can install 1 to many implementations. So the module has to search for implementation and tell the numeric script how many implementations there are and which are they. Afterwards, it compiles the benchmarking program, it runs the benchmarking program and collects the output, and finally, well, it stores the results. So we have a nice structure. Some more details. The input, as I said, is an XML document. In the XML, the user has to write which module has to be run, BLAS, LAPACK accuracy, and what are the test cases. Test cases basically are just packages. For instance, OpenBLAS version 0.2.4. And along with the package, each test case provides a compile time environment and a runtime environment, which are crucial for our implementation, for our tests. So it also has some other information which are not so important now. Then results, as I said, is an HTML document. And well, each benchmarking program outputs some date files, and the numerics use these files to generate plots and the document. And everything, as I said, is logged. And I will explain here some features of my tool. It's completely automatized. So usually when you do benchmark, you have to compile every library by hand, to compile the benchmarking programs by hand, to run them by hand, to collect the results by hand, to generate the plots by hand. This is completely automatized. So when you have numbench, you can write an XML input in, say, 10 minutes, and then you can let numbench run. It runs for 2 days maybe, but it's completely automatized. So it's a big gain, in my opinion. Most of the benchmarking programs are based on the BTL, so the performance, I mean, and it's a very high quality library. It's used by Hagen, it's used by many guys, so I can say it's a high quality library. The execution is sandboxed. You won't mess up your box, and everything you run is run in a specific environment, in a specific directory. So you don't have to be superuser, thanks Portage, because Portage allows a user to install a package in a different route. And then, well, if you get into troubles, you can use your intermediate results to restart the benchmark. You don't have to restart it over and over if you have problems. And as I said, everything is logged. And when I say everything, I say that we have lots of megabytes of logs when we run some benchmark. Now, these are some results. Okay, these are many different BLAS implementations run in an AMD CPU by Sebastian. You can see that yes, it makes sense to benchmark different implementation because the reference implementation is this black line on the bottom, and higher is better, so this is performance. And best implementation here seems to be ACML, which is the best implementation done by AMD, so yes, it makes sense. And you can see it's many times faster than the reference implementation. And wait, this is just serial. So if you if you go to multi-thread implementation, it will be even more impressive. And we can see that we have three very fast implementation, which are ACML, MQL, and OpenBLAS. I would say that, yes, these three libraries are written in assembly. So, and then we also have other implementation, Atlas, which is written in C. And what's that, Eigen? Eigen is written in C++. They behave well, but are not perfect. We can see that there are three very fast implementation out there. And interesting here is that OpenBLAS is the only open source implementation out of those three very fast libraries. Then, this is a very interesting plot. Here I compare the latest version of OpenBLAS. This is on my computer. It's an Intel Sandy Bridge CPU. The red line uses the new AVX vector operations, so new instructions, while the black line is the implementation that just uses the Nehalem instructions. So it's just the same version, just the same code, but with different instruction set. And you can see there is a very high, very impressive gain from Nehalem to Sandy Bridge. So if we compile this on our machine, the compiler can say, oh, it's a new Intel machine, so we can use this new set of instructions. But if we compile a package for other users and we cannot know what's the CPU on the other machines, we cannot use these AVX operations because we don't know if those CPU support this instruction set. So it makes sense to compile this library on the local machine, which is exactly what Gentoo does. You can see we have it's twice as fast, this red line. And here I compare Gentoo with Debian. Okay, there is not a lot of information here, but Debian is the latest beta Debian with OpenBLAS, latest OpenBLAS available on Debian. And the other curve is Gentoo, so latest Gentoo environment, latest stage 3 2 weeks ago, and latest OpenBLAS. And okay, we can say we beat Debian. We are faster than Debian when we go to big-sized matrices. But here, it's impressive. Okay, we have a very big gain here. And many operations, for instance, graphics, are here. Small matrices, and we are incredibly fast compared to Debian. Okay, I'm a Gentoo guy, you can say, oh, you're... But this is true, okay? This is just out of the box. Out of the box, Gentoo is that fast, Debian is that fast. Or that slow. Okay, these are other benchmarks. These are accuracy benchmarks. And you can see there is nothing very interesting here. Yes, there are a few libraries which are more accurate. What's interesting is that we can compare libraries for accuracy using numbench. So this is my final point. We have some goals for the future. We want to complete some modules. We have some accuracy tests to do, some numerical modules that I want to implement. And I also working on some web interface, so you can have a semi-automatic XML document generator and some automatized running system. What I want to stress here is that we need some users. Currently, I'm the only user, and Sebastian sometimes helps me, but we need more developers, but mostly we need more users. So if you want to use numbench, please do. We need some users. Because I know there are lots of bugs in numbench, but I can't find them. So I need some users. And I also want to stress this thing. NumBench was designed having numerical benchmarks in mind, but actually it can do a lots of things. Basically, it installs packages, so it enlarges packages with different environments. Then it searches for implementation of somewhat. So the module cares about these implementations. And finally, it generates some reports. So it generates some plots. You could do lots of things here. For instance, you could say, oh, I want to test, for instance, how big are the libraries installed by some package. So you tell NumBench, okay, this is my module for testing libraries, and you have to write a small file in Python to implement a module for your library check. And then you're done, and you can compare different libraries, different implementation of the same library, or you can have lots of possibilities. Just you need some imagination. Okay, this is all. You can find this project on GitHub. You can install it using the science overlay on Gentoo, and you can contact me. I'm Spyros. Thank you very much.
So, any questions?
Hello, I am also a Gentoo guy, but I would like to ask you, do you have any clue why Debian was slower than Gentoo?
Sure. Okay, sorry, this was the benchmark.
Yes.
You surely know that Debian installs binary packages. And when the Debian guys compile a package for the users, they have to choose a minimal instruction set for all users. And unfortunately, OpenBlast doesn't decide at runtime which instruction set to use. It decides at compile time, okay, we have such a CPU, so we can use such an instruction set. It uses very conservative vector instructions. So vector instructions, maybe not everyone here knows what a vector instruction is. But when we have a double here and we want to add this with another double, these are two different doubles. So we have 64 bits here. You can see here. This takes 3 cycles, I guess, of the CPU. A vector instruction is just the same, but this time we have such an sorry. Yeah, register. Okay, this is a register. So we have 264 doubles here, and we add this with another double, and so we do 2 operations in 3 cycles, while here we do 1 operation on 3 cycles. So if we use a different instruction set, we get something which is twice as fast as the basic things. So Debian does this, Gentoo does this. Actually, this is not really accurate, but this is just a very simple explanation.
This is just because of the CFLAGS and the difference between the hosts.
Yes, actually, when you compile something on Gentoo, you can choose which instruction set to use, and obviously your GCC or ICC or whatever will choose this one. While on Debian, you have to be very conservative, and you will choose this one because not every machine can do this.
Perhaps. Hello. Can you explain that big performance drop in Gentoo in these like sizes of?
No, I can't.
You can't.
Sorry.
Okay.
I guess it's. I guess it's something related to multi-threading, but I'm not sure. It could be cache effects. It could be something else. I can't right now.
And, as for the gap and slow down the performance, 7 years ago I made different tests, just like you did, and as I think is the problem is in memory and in processor cache. This is this gap is processor cache trouble. And,
You mean here?
yeah, you can continue your testing and you'll find the problem.
Okay, yes, it can be. It can be, sure. Well, sorry.
Any more questions? Okay, then I have one question. How do you expect to find users when your product is not in the main repository? And keep in mind that I'm the guy that creates the overlays.
Yes, actually, my project needs the scientific overlay because we are using, the scientific guys, Sebastian and others, are preparing a very nice blast pack implementation system for choosing the implementations, and my project needs this piece of software. So, until this blast infrastructure gets into the main repository, my project will stay in the scientific overlay.
Okay, thank you, Andrea.